Okay, correlation and regression. Okay, so we worked with the same example. We did a scatter plot and we kind of estimated the a straight line that approximated the pattern of that scatter plot. There are more precise formulas that more accurately enable us to compute the best fitting line for a particular data set. So anyway, we have these same variables we had before. Gestation or length of pregnancy and the birth weight. We're going to call the gestation the X variable, length of pregnancy the Y variable, and we want to write down an equation for predicting the birth weight based on the length of pregnancy. So for Quincy was born after 39 weeks. The birth weight was 104 ounces. Rochelle, born after 40 weeks, birth weight 100 ounces, and so forth. So what we want to do is first compute the mean and standard deviation of each variable separately. So this is what we were doing earlier in the course. If we add up all the X values, we get 390, divide by 10 babies, we get a mean of 39 weeks. And then we want each of these values minus the mean and square it. 39 minus 39 is 0, 0 squared is 0, 40 minus 39 is 1, 1 squared is 1, and so forth. Add up the total of this last column, the squared deviations, and we get a total of 70. And this standard deviation, square root of the total of that last column, divided by n minus 1, square root of 70 over 9. About 2.79 weeks, 0.78 and etc. weeks. Okay, so that's for the X variable, and then we do the same thing for the Y variable. We want the mean and standard deviation for the Y variable, so we start out by adding up all the Y variables at 1020, divide by 10, we get a mean of 102 ounces, and then we want each Y value minus the mean and then square it. So for Quincy, 104 minus 102 is 2, 2 squared is 4. Do that for each baby. Add those up and take the square root of the sum of that last column, divide by n minus 1. So square root of 2480 divided by 9, about 16.6. Okay, so then the next thing is to compute the z-score for each baby. So the correlation coefficient, this is a formula for the correlation coefficient. It's what's in this first set of parentheses here. You may recognize that as the z-score for F, right? Each X score minus the mean divided by the standard deviation. Here we have each Y value minus the mean divided by the standard deviation. Multiply those together. There's no operation symbol in between. Multiply them together. The sigma means sum. That means add them up, and then divide the whole thing by n minus 1. So that's the correlation coefficient. So for Quincy, it's going to be 39 minus 39, divided by the standard deviation, which was 2.78 something, and that gives a z-score of 0. And that's for Quincy's gestation z-score. Quincy's birth weight z-score, Quincy's birth weight 104, minus the mean is 102, divided by the standard deviation is 16.599 something. That comes out to be 0.1204 something. Multiply those two z-scores together for Quincy, and that comes out to be 0. Do the same thing for Rochelle. Rochelle's gestation z-score times Rochelle's birth weight z-score, and you get a number here for the product. These should total to 0. If we did everything correctly, the totals for the you could use that as a check for the z-score column should be 0. But this column total is what we're going to use in our computation. So the total here turns out to be 8.2 something, and so that's the numerator here, the sum of the products of the z-scores. and then divide by n minus 1. So divide that by 9. We get a correlation coefficient 0.912029185. So it's close to 1. It's a strong positive correlation. Okay, so the hardest part of the computation is computing R. Once you have R, then the slope is not so hard. Okay, so before we compute the slope, though, we'll do R squared. R squared, R times itself is 0.91 something times itself. It's 0.83 something. So that means that 83% of the variance of birth weight can be explained by gestation. Generally, R squared is the proportion of the variance of the y variable that can be explained by the x variable. Okay, so that's and there's different ways of computing R squared, but if you have R, then that's, I think, the most straightforward way of computing R squared. Okay, so the best slope, again, our calculator uses the letter A for the slope. I like the letter A for the slope. Some books use B1. Mathematicians like the letter M for the slope. If you have more than two variables, the reason they have a B1 for the slope. If you have more than two variables, then you'll have a B1, a B2, a B3, and so forth. So you can't have just one letter for the slope if you have more than two variables. But for two variables, I think A is fine for the slope. But it does. The letter they use doesn't matter so much. It's going to be the best slope is going to be R times the standard deviation for y divided by the standard deviation for x. So it's going to be R is 0.912029185. Standard deviation for y, we computed before, was 16.599866613, and divide by the standard deviation for x, which was 2.788866755. Okay, so if we do that computation, it should come out to be about 5.42857 ounces per week. And again, the unit of measure for slope is always y variable per x variable. Slope is a rate of change. It's not always emphasized. Okay, so that's our slope. And then once you have the slope, then you can compute the best y-intercept. And our calculator uses the letter B. Some statisticians like the letter B0 for the y-intercept. And it's going to be the mean for y minus the best slope times the mean for x. So this is mean for y was 102 ounces minus the best slope, which is 5.42857148, times the mean for x, which was 39, and this comes out to be a negative 109.714 ounces. Okay, so then we can put those together for the equation. Y equal ax plus b. So the y variable is birth weight, slope 5.42 something, times the x variable, which is gestation, plus the y-intercept, negative 109.7 something. And if we use this equation to predict Quincy's birth weight, Quincy was born after 39 weeks, so that's going to be 428571428 times 39 minus 109.7142857, and that should come out to be 102 ounces. So Quincy's actual birth weight was 104, and we just now predicted 102. So the residual or the prediction error for Quincy was 2 ounces. And then if we get the prediction error, we can do that same thing for each of the babies, get the prediction error. And the total of the prediction errors should be 0 for the best, if it's the best fitting line. And the other criteria for the best fitting line is the sum of the squared prediction errors is the smallest that it can be. So if you square each of these prediction errors, 2 squared is 4, negative 7.4 squared is 55 point something. Square these, add these all up. This comes out to be 417. And if you remember, when we eyeballed it, we got sum of squared predictions of almost 700. This is just a little over 400. So this is a much better, by this standard here, it's a much better fitting line than what we had before. Again, we can check our answer using the TI-30X calculator. Push clear while holding on, and then clear, second data, and then the stat menu comes up. If you push second data, the stat menu comes up. Push the right arrow to get 2 variable statistics, and then push enter or equal sign, and then data, put in all the data. You can go either left or right. You get to the 2 variable statistics faster if you go to the left. If you push the left arrow 3 times, you'll get the correlation coefficient R, 0.9 something. Looks like I'm frozen here. Okay. R is 0.9 something, and then push the left arrow again, you get the y-intercept B, negative 109.7 something. Push the left arrow again, you get A, 5.4 something. So those are pretty close to our answers. Sometimes you might be off by 1 in the last digit or something, off by a little bit in the last digit, but they should be pretty close to the answers they get from the formula. It depends on what kind of rounding you do on intermediate steps. Okay, some of the exercises in WebAssign have computer output and ask you to read the computer output to identify the different statistics from the computer output. And so this is actually, this output here is from Excel, and this is R squared, 0.83. That agrees with what we had before. This is R squared. The residual, this is actually the sum of the squared residuals. Sum of residual squared, 417 point something. And intercept, this is actually, that's B. And X variable, this is actually a slope. The slope, 5.42 something. So, so you know, you can, sometimes the computer output's a little bit cryptic, so it's it takes a little bit of getting used to, but you looking at this output, we can identify R squared, we can identify the sum of squared residuals, we can identify the best y-intercept and identify the best slope. The sign of R, you can also compute R based on this. R is going to be plus or minus the square root of R squared. So if you want to compute R here, it's going to be plus or minus the square root of the 0.83 something. So if you so before we found r, and then we squared it to get r squared, but you can kind of reverse that process. So if you do second square root 0.83179 7235, I get 0.912. 029185. But so which is it, plus or minus? Well, our slope is positive. R has to have the same sign as the slope, so it has to be it has to equal a positive 0.9. Same sign as slope. It has to have the same sign as slope. So you can they don't give you r specifically there, but you can compute r once if you know r squared and if you know the slope, then you can compute r. And that concludes this presentation.